Hello and welcome Duke alumni and friends to this session of the Duke Alumni Forever Learning Institute, an interdisciplinary educational program organized on a set of thematic courses. I'm Angela Greenwald, Assistant Vice President for Duke Campaigns, and your host today. Our program today is focused on accelerated materials discovery, partnering artificial intelligence and computation. This program is part of our materials science theme, where we discover how Duke is accelerating the discovery of new materials to solve our most challenging problems and build a better world. Moderating our discussion today is one of our very own, Amanda Randalls, the Alfred Winborn and Victoria Stover Moertke Assistant Professor of Biomedical Sciences and Class of 2005 alumna. I'd like to welcome Amanda to the Forever Learning Institute.
Great. Thank you so much. I'm so excited to be a part of this, and I'm very excited to see so many alumni joining from all over the country. Basically, I think this is a really exciting topic. I'm really looking forward to this panel discussion. As I'm sure you're all aware, there's a huge need for the next generation of materials. We're extremely lucky to have Duke researchers and alumni that are really at the forefront of this field. So today we've brought together some world-class experts to talk about different applications. And I think this is very exciting just because it does touch on like so many different areas, from solar power to agriculture to health. Over the last few decades, we've really seen the impact that the increase in computational power can have on the area of material science. We've seen computational modeling lead to significant advances in this field. And more recently, we're seeing this combination with machine learning, artificial intelligence, really pushing this field forward. And I'm excited to see what all the panelists have to say about these areas. So with that, we'll kind of throw it over to the panelists and let you guys introduce yourselves, say, introduce your name and your area of expertise. So we'll start with Ji.
Hi, everyone. My name is Ji, and I'm a fourth year PhD student at CS department, at Duke. And my major research is focused on the interpretable machine learning models. And it actually means the machine learning model not only can make predictions very accurately, but can also tell the user why it makes such a prediction. And I'm actually developing machine learning models that is interpretable and used for applications in material science, specifically for metamaterials. With some dynamic properties.
Great. And how about Mary? Can you go next?
Hi everyone. So I'm Mary. I am a postdoctoral researcher at the Mechanical Engineering and Material Science Department at Duke, and I work on metamaterials, mechanical and phononic metamaterials, basically that can alter how waves propagate through them. And I'm working in the same project as Je. So we work together on building interpretable machine learning models for materials design.
Great, and Johan.
Hi, everyone. I'm Johan Guillemino. I'm an assistant professor in the departments of civil and environmental engineering and mechanical engineering and material science. And I work at the intersection of computational mechanics and material science, using in particular AI and data-driven methods to basically accelerate computation and make them more reliable. And we apply those things to a very broad range of materials, but mostly soft biological tissues and composite materials.
And our last panelist, Willie.
Hello, everyone. My name is Willie Padilla. I'm a professor in the Department of Electrical and Computer Engineering, and I'm working on using deep learning for electromagnetic metamaterials, which are a type of photonic material that has many applications ranging from energy harvesting to lighting. And I'm excited to tell you today about some of our recent approaches on inverse modeling of such structures.
Great. Thank you all for the introduction. So maybe just to kind of kick things off, we see that machine learning and metamaterials is really a two-way street. It'd be great if can one of you comment on how do these work together, and also in that discussion maybe just give that baseline of what do we mean by machine learning and what do we mean by metamaterials to kind of kick this conversation off.
I can take that one.
Go ahead.
I think it's like I can get started. So I think the thing with AI in material science is that applying AI is not like just adding all problems in material science and just revisiting those problems through AI. So basically, you would use AI to do classification or to discover new things. So there is one way to approach this and to say we are going to use those techniques and again improve what we have in terms of predictions. And so you would just use AI in this one-way street. However, in many cases, most techniques which have been developed for AI cannot readily be applied to material science because materials, they behave in a given way, so they obey physical rules. And so this is not like classification of images, right? You have to satisfy those rules. So the two-way street comes from the fact that if you want to apply this in a reliable way, you need to account for those rules. And this is where material science can be used to basically develop new classes of techniques for machine learning. And this is usually called scientific machine learning or scientific AI, because this is, trying to leverage existing techniques, but make them relevant to material science. And I think it's a very good way, it's a very good synergy between those two classes of techniques. I don't know if anyone else wants to elaborate on this.
I could put in something here. So yeah, definitely. And I think Jay and I in our project, we have witnessed some example of this happening because in our project, we were looking for global patterns that materials could have in order to control the wave propagation in them in some way. And it so happened that our collaborators and Jay, they could have some input on this, and they even developed a new method that is specifically tailored to handle this problem. So just one example of this.
And just to follow up on that and kind of building, I know, Jay, you mentioned even in the introduction that you were very interested in interpretability and understanding of the machine learning application. Can you comment of how we go from making this just like a black box where we don't know what's happening on the background to making sure it's something that is interpretable and actionable?
Yeah, that's sure. So basically, for machine learning, it's basically you have a whole bunch of data and you have some input and you have some output, and the output could be like material science property, and you try to learn a mapping between the input and the output, right? But the problem is I think lots of the very popular methods like deep learning, they're basically considered as black box because the function is too complex. Like the mapping from the input to the output property is too complex so that no one can actually understand what's happening here. So this is very problematic for application like material science because it's a science. So you want to really know why that actually happens. So, for example, in the project we actually working on, the method we developed try to identify some global patterns in the material design that is associated with the target property, and this kind of pattern is actually visualizable. So you can actually directly visualize what kind of pattern in the design is associated with the property, so that there's some interaction between the domain experts like Mary with the machine learning algorithm, so that people can know what has been learned in the model.
And then maybe coming back out a little bit, it'd be great to hear a little more about the applications that you guys are focused on. So maybe starting with Willie, just a little bit more detail of what application area are you most interested in, and kind of a little more on that end.
Sure. So I can give an example. As Ji just told us, these deep learning models are very good at figuring out the underlying equations that connect you from some input to output. So one example of something that we're working on is we're designing a metasurface, which is a single layer of electromagnetic metamaterial that gives rise to a certain emission pattern. For indoor lighting, you might want to emulate sunlight. And so we want to be able to heat up that structure and have it emit only in the visible spectrum without having any of the infrared radiation that incandescent light bulbs have, for example. So on the input side, we have a metasurface, which might have some structures, and their geometry sets their spectral output. And so you can look over some parameter space of geometry. The deep learning can learn those inputs and match a solar spectrum on the output side. And so that would be an application that we would do in deep learning to use deep learning to solve that particular problem.
And maybe in that space, Johan, if you don't mind giving a couple more details on your application area as well, and then we can dive into more of the methods in a second.
Okay, so I have two applications in mind. One is in a project funded by NSF. We are looking at the mechanics of vascular tissues. And those tissues are very complicated in nature. They are very multiscale, very anisotropic, meaning that they basically behave in different ways depending on how you apply forces, essentially. So they are very complicated to describe. So historically, this was done by making some assumptions and trying to fit some parameters. And what we did is that we have been working on trying to revisit those models using machine learning techniques to basically be less, not to depend too much on the choices that we make, but have some sort of generic catalog of description for the material. And the second application that I have in mind is when you do experiments and you have limited resources. So you can basically make 5 experiments, but you would basically need more than that. And one way to use AI is basically to use AI to generate new data sets based on those limited data. And so we had very good results, for instance, if you look at acoustic materials that can be used for insulation, for instance, and only with 10 samples, we were able to predict the behavior of the material over ranges that we never tested experimentally, which is actually very great, very good, because we want to go beyond that. And so I think that's a very interesting question, because usually deep learning methods are meant to perform in the big data limit, which is a limit of like Google. When you Google something, you have like billions of images. So basically you can process, this is a big data setting. When you do material science and experiment and computations, usually you don't have that. You can have like 100 data points, but that's pretty much the best you can get usually. And so those techniques can be used to enrich and enhance the description and go much beyond what we used to do in the past. Those are just 2 examples.
I think that's a really good point I feel like when we think of applying machine learning, we always think of the big data side, and you need to have like the very large scale. How do you even, and anyone kind of comment on this, but like, how do you really get involved? How do you figure out which methods and which techniques, and how do you bring, machine learning techniques to problems that may not have thousands or, the scale of images and data sets that we're kind of here conventionally, like you're mentioning. What are the tool sets, and I think even more broadly, especially at Duke and kind of across the projects, of like how it's a very interdisciplinary project with bringing in the machine learning and the domain side, and kind of, can you guys comment on both the big data aspect and how you bring in, how do you connect to these 2 fields?
I can make a comment. So in contrast to what Johan just mentioned, we in my field do indeed use big data sets. What we're doing is doing numerical simulation, which solves Maxwell's equations. And so those are very accurate solutions. So we simulate a number of different inputs and outputs, and from those ground truth pairs of geometry and simulation, we use those to train a deep learning model. And so typically the simulations might be something like 20,000 to 80,000 simulations, numerical simulations, that we then use to train a deep learning model.
And what's the scale of the data for that? How do you need the cloud to be able to process this, or where, how are you handling that scale of data?
So those simulations, we might be able to do something like 1,000 to 5,000 simulations per day on just kind of a normal server machine. And so even though it takes maybe a couple of months to build up the data set, there are other things that we could be doing in that meantime, such as working on the deep learning model or doing other things as well. So it takes a bit of time to build up the data set. But once we have that, we find that kind of a conventional feed forward neural network works very well for at least the data sets that we're looking at.
And that leads into, I think we have a great question from the audience of, this kind of builds on what something you said, Johan, of like, how do you confirm the efficacy of the projections in the areas you can't test in? Which is a great question.
Well, in this specific case, we are cheating a little bit because we have more data than we are accounting for at the training stage. So we had, let's say, essentially we had 10 samples, so that's a frequency response. And so, those are materials where you can basically change the size of the pore inside the material. And so we basically used 8 responses to train, and we have been testing 2 of them. So we had the data to basically judge whether or not the technique was relevant in this specific case. Otherwise, there is no magic doing extrapolation, right? You need to have some, but there are things you can do to make things a little bit more robust. Usually when you have, again, you have 2 very different regimes, the big data limit and the small data. Usually in science, when you have a lot of data, you let the data speak from themselves and you are focusing on the architecture and training. When you have a very small data set, you need to have an input. You need to basically regularize the problem by putting a little bit of physics or mathematical modeling that is essentially going to compensate from the fact that you don't have those data. So you cannot apply those techniques brute force. You need to do that. You need to have some sort of a pre-processing before you can apply those techniques. And then regarding testing, again, usually you try to get a bunch of data to test the formulation.
And I wanted to ask a question, it's a little bit changing gears slightly, but I think the alumni side may be interested of, I think this is a very cross-cutting topic that is, kind of supported by new initiatives at Duke, like the DST and the science and STEM initiatives. Can you comment on some of the initiatives around Duke that are really supporting, this cross-cutting part of the machine learning, the metamaterials? Are there institutes, programming initiatives, where are you seeing support coming from Duke as a whole for this type of work? Or I guess in general, also, are there institutes or initiatives that people should be looking at to find more information, find other researchers that may be in this area as well?
I think, just to get started on this, I think one of the main issues when you try to apply those things is basically training of students and professionals, because usually when you have a computer science degree, you don't know what materials are, and when you are a material scientist, you don't know exactly what those algorithms and black boxes are doing. So recently at Duke, we were awarded this NRT, this traineeship program, where we are essentially taking students, pairing students from CS, computer science and material science, and training them all together. So people from CS would get a training in materials, people from material science would get a training in CS, and basically work through projects. So that's a 5-year NSF project, and the goal is really to advance the next generation of engineers that would essentially master and really understand the field and at the intersection of those 2 things, just moving away from black boxes and understanding the material science standpoint.
Are there any other initiatives you guys think we should comment on or make people aware of? I'm not sure. I'm trying to think of ones I know. Yeah, Willie, you look like you're ready to jump in.
Yeah. So there is Athena, which is an NSF program that's headquartered at Duke. It's a multi-university transdisciplinary AI center. It includes 7 academic institutions: Duke, Yale, Wisconsin, Michigan, Princeton, MIT, NC, A&T. And then there's 5 industry collaborators as well: AT&T, Microsoft, Motorola, Edge Micro, and Five9.
I don't know if any of you are involved directly with the IID. There are other, there's the Information Institute at Duke where there's more work going on, a lot of interdisciplinary collaboration on the machine learning with materials. I think there may be, Johan.
Yeah, I mean, I'm part of the IID, and IID is essentially putting people interested in the intersection in the same building, like a computation slash data science building, where we have people doing like a typical AI, and people working like myself, but others in computation and material science, and basically trying to advance those fields. And we have a couple of projects collaborating all together, and I'm trying to think about something more like giving you an example on this. So, for instance, when you have we have collaboration where with people doing generative models. So if people are developing, mathematicians are developing techniques again to sample data. When you have a data set and you are trying to essentially to generate new data according to those things. And so we are working with mathematicians and statisticians to basically apply those techniques. And again, in this two-way street way of thinking, trying to develop the new techniques at the intersection of those two things. I don't know if anyone else has another example in mind.
And Johan, was the AIM program the one that you mentioned as the traineeship?
Yeah, so the AIM program was the traineeship. The AIM is like AI for material science. I should have said that. And it also comes with a lot of experiences for the students. So they're gonna go in the second year. They're gonna go for internships, 2 to 3 months internships at national labs and private companies. And again, trying to spread the word and developing those techniques.
And then coming back to the scientific side of it, Thomas had a great question of saying, can you remind me where the material modeling's applicability is? So kind of, I think that's aimed either at Willie or Johan, if you can just kind of sink us back into where are we actually applying these material models? Or maybe Mary or Jeff, feel free to jump in on.
Yeah, I could say something. So in our project JNI, we are actually looking at materials dispersion curves. So basically, what that means is if you architecture a material in a certain way, put some materials together in a certain way with certain material property distribution and certain geometry, how mechanical and elastic waves would propagate through them. And this might seem a bit of an abstract concept or topic, but it can actually have applications in anything that is affected by vibrations or waves. Like, for example, you can think about it for vibration isolation. You can think about it as the next technology that would go in your car to offer some acoustic isolation with lower weight materials or lighter materials. You can also think about how you could apply this to possibly attenuate seismic waves to lessen the impact of earthquakes, for example. So, yeah, so basically, at least in our case, any area that could deal or do with vibrations or waves could be a potential application for our methods.
Maybe following up for both of you and kind of tying into the last conversation of can you guys comment on kind of the training you've been exposed to and kind of received here, and maybe also, what kind of next generation technology are you actually getting exposed to and getting to actually work on through this training, and maybe comment a little bit on your experience.
Would you like to start, Joe, since you're also an AIM fellow?
Yeah, definitely. Yeah. So first, I want to copy the link of the AIM program. So here's a link for the AIM program.
Thank you.
And so basically, so the AIM program is trying to train the members or the students to get interdisciplinary professionalship in both AI and material science. So for example, for me as a CS student, I don't really know much about material science. So I first need to take intro material science course to know the very basics about material science. And then we have some application of AI to material science course where we know some very basic applications and know about like the projects people are working on here at Duke using AI for material science. We will also have a project course where we work on our own research to develop our own models or techniques to apply AI for material science. So that's the basic training we got in the AI material science program.
Yeah, for me, since I'm a postdoctoral fellow, so I sort of joined into this after I got my PhD. So there's a lot of exposure, of course, since we're working on interdisciplinary projects and like with collaborators. And also, yeah, I try to also like get in as much as I can from our collaborators and also the courses that are open.
We have another question from the audience. So I want to jump into that. Walter's asking, I'll just kind of read this out. There's two major parts, so feel free to like listen to both and jump in and answer either one. We know that traditionally machine learning has really been black boxes, but two kind of follow-up questions that does making the process transparent or reversible reduce the efficacy of the machine learning system? And second, are there rules of the computation that work kind of like conservation laws or the Heisenberg uncertainty principle to limit what can be known?
Maybe I can answer the second question first. It's known and proven, in fact, that a single hidden layer neural network is a universal solver. So as long as it's trained on accurate data, it can solve any forward function. So that's proven. So that's the answer to the second question. The first, and maybe those of you working on interpretable deep learning can answer that. But I'll say one thing, which is that there are neural networks which are invertible, so invertible neural networks which you can make it go both directions, and those work decently for problems which are not ill-posed. So those work good for well-posed problems. This is a mathematical definition, but there are a large class of problems that are interesting, which are called ill-posed inverse problems. And for those types of problems, it is difficult to make it kind of a dual way or a kind of invertible neural network. So those are challenging to solve. And their deep learning has made an impact, however. So there are so-called deep inverse methods that are based on deep learning that have solved those sorts of challenging problems.
Yeah, I think I can also comment on the first one because I'm working on interpretable machine learning. So theoretically, if you consider like the entire set of models, of course, like the best model in the entire set of model should perform a bit better than the set of interpretable model or transparent model. But the problem is there might exist a very large set of model that can work well on the problem. So this set might contain a lot of transparent model. So in our experience, although theoretically, like the black box model might perform well, might perform better than transparent model, but the performance of those two models are very close to each other. So if you just consider accuracy, they are not very different from each other. So this makes transparent model or interpretable model being very useful in practice because the accuracy or the performance is actually on par with the best black box models.
Maybe just before we dive into any other questions, can you just take a second and really define what we mean by interpretable machine learning, just to make sure that everybody's on the same page?
Yeah, definitely. So interpretable means the prediction process or the decision process of the machine learning model is understandable by humans. So for example, a linear model, it is interpretable because you know how it actually makes a prediction. And the definition of interpretability is actually varies from field to field because how you understand the problem is defined by human in that field, right? Because whether something is understandable, it depends on how human understand the problem. So, so for example, in material science, something might be understandable is when you show the model decision process to material scientists, they say that this actually makes sense. And it actually varies from field to field.
That's incredibly helpful. Thank you very much. And so I want to just take the conversation a little bit back to the application space and kind of talk about, for all the alumni on the call, of how could these kinds of models affect us on a day-to-day basis? And can you comment on like some of the other exciting areas, like what Mary was mentioning with the earthquakes, and like where do you see this applying? I think both, where does this show up on a day-to-day basis? And then even getting into Johan, when you were saying, we think of this as applying to big data problems. It's not necessarily big data. It could be with smaller, how do you pick a good, what makes a material science problem suitable for, marrying it with the machine learning approach? And where are we going to see this really making an impact on an everyday basis?
Maybe I can answer the last thing that you said is, we were, at least in my research, we were brought to deep learning kind of naturally. And that's because we were studying a particular electromagnetic metamaterial that was where the physics of it wasn't well known. And it was a highly nonlinear problem. And so we used the conventional methods that we were used to try to solve this problem. And we largely failed. So it was very difficult to understand the physics. So the physics wasn't known, and it was difficult to understand how to make any progress in this parameter space. And so we turned to deep learning, and it somewhat trivially solved that problem for us. And so I was kind of a believer right from the outset. So I would say that not every problem should be attacked with deep learning. There are, if the physics is known, if there's an equation that's known and it's exact enough for your particular application, then I think that's the quicker route often than building up a machine learning model. And so there's a trade there somewhere between what physics is known, and it seems with what Johan was saying, it would appear that some of the physics is known, and so one can do a bit of simulation or experiment to make some headway, but there's some crossover point there where it becomes useful for new materials, in fact, where the physics isn't known, or where there's a highly nonlinear system where it's so complex that you can't sweep over the parameters to make any headway, and there's no guidance or intuition to guide you. So those are the cases that I believe that you truly need deep learning approaches.
Great, thank you. And then, can one of the other three panelists comment on either adding to that or comment on where you think we'll see this impacting us on in our everyday lives?
Yeah, I think what Willie said is very important, because in most of the discussions we assume that the physics is known, and we think about AI as deep learning. So we're gonna take an equation that we know, and it has a lot of input parameters, and we're just going to make the prediction faster and in some accurate way. And there are cases where the physics is not known, and you can also use machine learning techniques to discover the physics. So instead of, let's say, solving like the equations we have known like since high school, like Newton's equations, okay, so you know that equation, you just try to solve it fast. You can say that we're going to have a dictionary. We're going to start with a dictionary of functions and a very big dictionary, a big bag of candidates. And machine learning is essentially can be used to build the equation describing the physics. And I think this is a very interesting way to apply this just beyond deep learning, discovering the physics. And likewise, here we are making predictions, but you can also use AI to design in a much better way, because when you think about the design, for those of you who are not from material science, you can think about the material as a DNA. Okay, so it's basically, those are building blocks, and you basically arrange those building blocks in a given way. And so you have a lot of combination. You have a huge combination of possibilities. And so from a mathematical standpoint, usually the design is combinatorial. So the number of solutions is absolutely huge. And so you can use machine learning also to explore those solutions. And you can try to do that in some interpretable way, which I think is another way to apply AI, not only deep learning, but also AI. I also think that applying machine learning to enhanced data sets through generative models is very interesting, because it's really opening the door to solve ill-posed problems. Like, for instance, you have a cardiovascular disease and you make some non-destructive testing on this, and you have one data point, something like that. And it's very ill-posed because the body is very complicated and things like that. And this is where you can use AI to somehow build knowledge and refine the physics and hopefully make an informed decision regarding diagnosis and treatment. I think what is very interesting, like tomorrow, using those techniques where you can design fast, you can predict fast, and you can embed this, you can endow this with the statistics, when the idea would be you go to the hospital, you get some measurements, and we can make a decision in 2 hours, and then we can print whatever we need and just put this in your body, right? So that's going fast and going informed is, I think, where AI, one domain where AI is going to really shift engineering practices.
So that's perfect. That leads into my next question perfectly. What do you guys, and I want each of you to comment on this. So, like, what are you most excited about in your research right now, and what do you think are the most exciting possibilities for this area? Kind of getting into the heart of what gets you out of bed in the morning. What do you think is most exciting about what you're working on?
So I can mention the thing that I am excited about currently is deep inverse modeling. And so I'd mentioned that electromagnetic metamaterials, you can very somewhat trivially specify a geometry, some structure, some material, and then learn a forward model, a deep learning model that correctly may calculate what the spectrum of that is. Let's say electromagnetic spectrum. What would be more interesting is to specify a particular spectrum that you want, some desirable, and to have the deep learning model tell you exactly what geometry you need to solve that problem. That's an inverse ill-posed problem that I mentioned. Those are extremely challenging, but recently, over the last 2 years, us at Duke have made great progress to solving that using a deep inverse method. And so we're really pushing this, and we've benchmarked and tested that against other state-of-the-art inverse approaches, and have shown that it works really good in comparison to current state-of-the-art. And so, for example, in the application that I mentioned for lighting, one could specify, I want this particular spectrum inside of my house, and it can show you the geometry of a metasurface that would yield that response. And so that's something that we're currently working on through the Department of Energy.
That sounds like you've made a lot of progress at this stage. Do you see achieving that goal as something that's a year out, 5 years out? What's the kind of scale on that?
Yeah, it's a good question. At least the design that's being predicted in these is somewhat challenging to realize. So another thing that we're trying to do is to add, in this inverse approach, to add another knob or another parameter that pushes it to something which is more fabricable. So the design is somewhat challenging to achieve. So another kind of metric that we want in this inverse modeling is to make sure that it's as easy to fabricate as possible. So the design that we have can be fabricated, but it's challenging. It kind of pushes the limits of nanolithography at present. So we could be, I think, realistically, something like 5 years out, I would say, to put a number on it.
I do a lot of work in the biomedical space, and constraining the models of it's very exciting that we can predict new materials, new drugs, new areas, but then you also have to figure out what is actually synthesizable and what can you make, and that's an interesting another part of it that is really useful. And Je, I know you were ready to jump in on what gets you out of bed in the morning. What are you most excited about?
Yeah, the thing I'm most excited about is if our machine learning model can discover some new knowledge, new domain knowledge from the data. It's like for a human, for a researcher, maybe in material science, the person can only look at very few amount of data, right? But the machine learning model can look very large data, and maybe the machine learning model can discover some new knowledge in the domain, and that's really, that's really great. And this is something I hope my model can actually discover.
Yeah, that makes sense. That's really exciting. Maybe that leads into Mary, if you want to comment
Yeah, actually, I totally agree with what everything that was said right now, and also like discovering new knowledge and also the inverse design problem. And I might add that till now, there are a lot of inverse design problems that largely depend on intuition and trial and error because they are very complex to tackle systematically. And if this new knowledge that we uncover could lead us to some systematic rules to tackle these largely intuition dependent problems, that would be for me a great win.
And that brings us to you, Johan. What are you most excited about in your world right now, and kind of what do you see as the implications of that?
Well, I'm really excited about computational bioengineering, and in particular, designing materials and diagnosis and all that stuff, integrating patient-specific data, which is, I think, still not the main, practice in the field. And so working, like, for instance, like, again, if you fracture your rib, having a decision made very quickly and print a plate that would be made like just for you, like, that's going to heal the best way, accounting for processability, just as Willie has just said. You want to control those things. It's in vivo, so it's going to degrade over time. So a lot of multi-physics modeling inside. So that's really something exciting. And I really think that within 5 to 10 years, we're going to have a lot of new things coming out in terms of techniques, computations, blending computations, because usually AI in terms of the Earth has been applied to the processing of data, but I think still very rarely to everyday practice. You go to the hospital and things are going to be processed. You're just gonna do things in the best way for you. And so that's more like the application type of things. And the other thing I'm really excited about is tackling things where the physics is wrong, like it's wrongly described. So and trying to basically correct this with AI. So coming up with the right equations from data instead of assuming some models.
Yeah, that makes a lot of sense. And I realized I kind of skipped over and want to circle back and just kind of follow up with Mary a little bit more on that. I liked your comment on building the intuition. Hoping, could we just delve a little deeper in that as well?
Right. Like right now, so it really ties into a lot of elements that were mentioned just now. So about being able to, like what Willie said, if you would like to impact a certain spectrum, so how would you design the material geometry and composition to meet your target properties? And then also it ties into what Joe mentioned about interpretable principles that would sort of educate you as you go, like you see the results of your model, what you learned, and if you can deduce something from it. And I think, at least in my field, that like there are some problems right now that largely still depend on the educated guess of experienced designers. And you really have to accumulate this experience and to try a lot before you get something that's working for you. And as you can imagine, this is very like time costly, and also it uses a lot of human resources. So if we could somehow reveal interpretable rules that could tell us how to tackle such problems that are still largely dependent on intuition. So I think this would be great. And I don't know if this answers your question or like.
No, that was great. Kind of building off what Mary had just said with, kind of going on the idea of the barriers coming from like the starting point and trying to use the educated guess to go with. What other barriers are you guys, coming up against, and how do what do you see as the barriers in this area? And anyone feel free to jump in. Yeah, Mary, go ahead.
Yeah, so I would mention maybe a couple right now. So in my field, at least, there are right now two main problems, basically. So first, in vibrations, most vibrations around us are low frequency. And how, like, if you were to isolate these vibrations, you would need to build huge structures so that you meet the same. So like those low frequency vibrations, they also have incredibly long wavelengths. And right now, so in order to interact with those incredibly long wavelengths, then you need to build incredibly huge structures to interact with them. And right now, like over the past decades, people have been learning more about how to actually be able to interact with those long waves, but with smaller structures. But this is still a process that is largely dependent on intuition. And the challenge here is to reach as like small frequencies as we can get with smaller and smaller structures. So this is one problem that so far I have seen being driven by human, like intuition, and even if it's like systematized, or even if it's achieved computationally, it usually takes a little bit of nudging. So that means that you really know what you're looking for, where you're looking for it, and you are unable to explore new knowledge in that domain. And the other problem is to how to be able to transfer information via waves in a reliable way. And this has also been, as far as I'm aware, been also very intuition driven.
Right. And I think those are really good points. Are there other barriers anyone else wants to call out in different fields before we move to a different topic? Or
I can mention that a limitation in my field is the data bottleneck. So I mentioned that we're doing these numerical simulations, and they may take a couple months. For more challenging problems, the simulations take longer, and therefore it's difficult to build up a training set. And so the data simulation bottleneck is kind of the main challenge in my field of research. So we just need more computational resources. Those are things that kind of benefit and aid, but it's still a fundamental limitation.
Yeah, Johan.
I think on my end, I think the integration of physics is still an issue. So as of now, the way this is treated is that when you train your neural net, if you think about deep learning, you are going to basically minimize the discrepancy with the data. And what people did, most of the techniques, they basically minimize the discrepancy in the physics. So you take the equation describing your physics and you say, over a finite set of points, I want my neural net to satisfy my physical equation. But when you do that, essentially you are doing this over a finite set of points. So if you cannot guarantee that at any point in your domain, the physics is going to be satisfied. And so I think, again, trying to build new AI representations that would be consistent with the physics almost everywhere and almost surely is I think a big challenge. And in particular, if you think about ill-posed problem and smaller data sets, that's very challenging.
That's it. Yeah, I'd love to kind of follow up on that a little bit on just the methods. And I think conventionally, when we first started thinking about machine learning, there's a lot of, it was great for things like classification. And now we're seeing more of like the pins or the physics inspired or like the neural networks. And how do we, I think this is in the last 5-10 years, even there's just been so many different methods and algorithms and techniques. And like Willie, you mentioned having like the one hidden layer. And, I think any comments on just how would you get, how do you figure out what the right method is for the problem you're trying to solve? And coupled with that, I think, what methods do you think we need? Like what's still missing, which I think leads into, builds off of exactly what you were just saying, Johan. But yeah, how do you identify the right method, and what's still lacking, and where do we need to develop on the algorithmic side?
I can just say a few words. I think regarding the techniques, I think training is really a key aspect of using AI and ML, because it's very easy to go on the web and download like those toolboxes, and you can actually get nice results. Like, you're gonna fit your data points, like, in most applications. But I think understanding that AI, machine learning, they can be seen as part of like, broader fields, and you need to have a background in statistics just to know what you are doing and know, because like there is like interpretability, but just knowing like how to interpret those results, like knowing how they behave. Like if you take a neural net and you feed a function, and if you make a small perturbation of the function, your neural net is going to go all over the place. So it can be very unstable and all those things. So I think training, and I think understanding those techniques in deep before diving into applying them is really a key thing. And I think this is why I think the AIM program at Duke is really is a very interesting program, and where Duke is really leading the way, just educating people, more people, knowing how to apply this in some informed way.
And I know we're running out of time, but I do want to just push that a little further and ask, and maybe just if we want to put them in the comments as well. I think training is very important. So if the alumni or the people on the call want to get more information or learn more about like this area, are there books or online learning that you would recommend, or where would you suggest to start with improving the training in this area?
Well, I'd say that there are a lot of resources out there. I think you have like classical textbooks you can use. I think starting with a little background in statistics and then moving into those techniques like machine learning and deep learning techniques. And there are like Duke has a lot of resources you can find online, for instance. Part of this initiative where you can find like lectures online, even on YouTube. I know that Cynthia, for instance, has part of a lecture available online, and just educate yourself, make some tests, take Duke students for internships, and just moving forward like that. Learn every single day.
I will say I know there are classes. I'm pretty sure in Duke's Coursera you can see like Larry Cairns and Dave Carlson have a class on machine learning that's absolutely fantastic. And there are definitely a few like applied application focused machine learning classes available through the Duke Coursera.
I was going to just mention to you that there was a question that came in there from Walter Henderson.
Yeah. Hopefully, yeah. If we can take a second and answer this quickly. I know we're hitting up on time.
Sure, I can.
But it'd be great if you want to summarize it, because it's a very long question. But if you want to summarize an answer, that would be fantastic. And sorry, Walter, for not getting to that.
Yes. So Walter is asking. A lot of us are working on the wave equation, solving the wave equation, and if there's something special about that. I think the answer is no. As long as you have ground truth data and you can simulate or have experimental data. Or as was pointed out in the beginning, if you have access to big data sets, such as pictures of cats, anything that's ground truth, you can train on. And so if you can have enough data, then the deep learning can learn a forward model from that input to output. So there's nothing special about the systems we're looking at. It can be applied to any system where you have large quantities of ground truth data.
So we'll kind of pause there. Yeah, thank you all for letting me be a part of this. I really enjoyed the conversation.
Yes, thank you all. Thank you, Amanda, for moderating this great discussion. And thank you to our panelists, Johan, Willie, Mary, and Jia, for a great presentation today.